But when I was done with it, we didn't let it.
All right, so I want to talk about ODP 451. I want to talk about some more Linux stuff and such. Any questions up front, though?
It's warm in here. That's not a question, that's a statement.
It is a statement. So apparently nobody is going to do anything until it's above 78. I guess if the cutoff is 76.8, but I can open the door and try to cool it down.
Tony, why did you do that? Why'd you put it funnel? Yeah, you did. I did not.
Oh, yeah.
No, I still have the...
Not that warm.
Like the argument is 2.
Thanks, Nick.
Yeah.
I've had a pencil on it. Last for years.
Oh, this is...
Yeah. I saw it last night. It struck me.
Because like if I did...
All right, so let's look at ODP 451. Let's just wrap that one up.
With this?
Yeah. Oh, okay.
So here's an example of code that would work for input.c. I included standard I/O because I'm using stdin, and that's defined in standard I/O. And I'm using fgets, and I'm also using string length, so I included string. Those includes, if you don't need the include, but you put it in anyway, you're probably okay. If you're pretty sure you don't need it, leave it out. If you're not sure, you can always leave it out and try compiling. But if you happen to put it in, you don't need it, it's usually harmless. But it's extra stuff to compile, and it's extra visual clutter and so on. So I've got my 2 includes. My function is called input. It's declared to be a void, and this is sometimes confusing when we say void function. Say it's taking an integer n. It's not that it's returning something of type void. Okay, if we say int, we expect function to return an int. If we say car, we expect function to return a car. If we say void, it's not really returning a void. Okay, void is kind of a hook that we're using to say there is no return value. Okay, so it's sitting where we would normally put down the type of the return, but it's actually meaning there is no return from this function. So things go into the function, right? We pass in one integer, and it's not passing anything back to us.
So if you use return in that, would it just exit the function?
If you use return, it'll just exit the function. If you say return number, it'll complain when you try to compile.
Oh.
Was that happening?
That also happened.
Okay, yeah. And if you say int, and then you do a return without a number, it'll complain that you're not returning something. So if it's a variable type, you've got to return that type of variable. If it's void, you can return without naming anything. And then the argument is just the thing you're passing in. So a void function I would run just by saying name of the function and, you know, whatever the integer is I want to pass to it. A number or a variable or whatever. Alright, so input's the name of the function. It's taking a character array, a string, and it's not returning anything. And the goal was to use fgets to read input from the user, chop off the last character, and then load that into the argument that was passed in. So I could do an fgets into a temp array and then copy temp into arg. Some people did that. Or I can just use fgets directly on arg. Either way is fine. So I did the latter. Okay, so fgets. First argument to fgets is where you're putting the stuff that the person typed. It's where you're storing the input. Second argument is the length of that storage area, and the third argument for now is always standard in. That's where you're reading from. So this call to fgets says read up to 120 characters, store it in that arg, which was the thing that was passed to the function, and then we chop off the last character. So arg is the input string. String len paren arg close paren is an integer. It's the length. It's how many characters are in that string. Subtract 1 from that integer. That gives me a different integer, which is the index of the new line. And then access that element by putting it in brackets and put that after arg. That refers to the new line, and then set that equal to a null. So you write this and you want to test it yourself. How would you write a main program? Let's call this mymain.c. So I'm going to do some prints. So I'm going to include standard io.h. I'm just going to make this a main. Alright, so input.c, I have to call it, I have to pass it a character array. And input is going to store the user input into that character array. So I need that character array to not just be syntactically, this is a character array, it's actually got to have some space in it for the user to store something. So I'm going to set that up, and I said you could assume 120 characters is enough. I'm just going to say character temp 120. And then I'm just going to pass that to my input function. And then I'm going to print out temp equals, and I'll print out the value of temp as a %s inside angle brackets. And if I try to compile this, okay, so here's how I would compile it. Alright, gcc-o, my main is going to be the output file. mymain.c is the main program I just wrote. Input.c is the function that I'm interested in. If I try to compile this, I'll get a warning. I won't get a warning. That's annoying. Well, I should have gotten a warning. Even if you don't, prototype your functions. So what is prototyping? It means that we're calling a function named input. We haven't told the compiler what input is. The code for input is in a totally separate file. So how is the compiler going to know what I mean by input parentheses temp? We have to define what the function input looks like. So this line right here is what we call a function prototype. It says input is the name of the function, it expects a character pointer, and it doesn't return anything. Okay, and that matches the way that we actually write the function input, which is void input char star variable. Okay, this is a little bit like a system diagram in like 12250. This is the actual circuit. This is the thing that has all the code that makes the function do what it's supposed to do. This is like a 40,000 foot view of the function. What's it called? What types of things go in? What type of thing comes back? But it doesn't actually have the code that does all the stuff that this function does. That's in a separate file. So this is just like telling us how to connect to this function, telling the compiler. Does that make sense?
Yeah. What did you call it again?
Function prototype. Yeah.
You only need to do prototypes when they're in a different file?
No, you need them everywhere actually. If you have any functions defined, you should prototype them at the top. And sometimes if you don't do it, it won't complain, it'll make assumptions, but it's cleanest to just always prototype them.
Okay.
And this stdio.h is primarily a bunch of function prototypes for things like printf and scanf and so on. Because we don't write the code for printf, right? So somehow the compiler has to know what kinds of things are going to get passed to printf. Well, that's set up inside stdio.h.
Is there a way to look into stdio.h?
Yeah. So your include files are under /user/include. So there's the mythical standard.io.h.
Can you modify this and add your own?
You could copy this and make your own version of it and then include your own version. And use quotation marks instead of angle brackets. This thing is a bit of a nightmare to try to reverse engineer. For one thing, it's got all sorts of includes inside, like include features, include standard def, and so on.
Can you find all those?
Yeah, they're all under there. So like include bits /types would be user/include/bits/types.h. And they also use these macro definitions where we have defines and so on. So there's a prototype for fscanf. It's externally defined, it returns an integer, it expects various pointers, and there's a ... because we don't know how many arguments it's going to have.
What was the file path again?
/usr/include. And yeah, this will make one's head spin pretty quickly. All right, so let's run this main program. Let's compile it and run my main. And so now I'm inside my input function. It's waiting for me to type something, and I'll say hello, and it tells me this thing that it returns is hello, and there's no new line at the end, right? Because the bracket is right there after the O. And I know that fgets puts a new line on the end, so this was apparently successful in chopping off that last character.
So I went to open up stdio.h
Mhm.
and I got that swap error.
Oh, maybe because I was editing it. Try it again.
Okay.
Or somebody else has it open.
Oh.
All right, so questions on 451. You can ignore that error. Someone else probably opened it.
If I open a read only, then there's nothing there.
Let me see your commands. Don't tell you what you want to write it. /usr/include.
There we go.
Did we talk about the file system in this section?
I think briefly.
No, we haven't.
So you log in, you're in your home directory, right? I'm on the Linux server. My home directory is /home/nick. Your home directory is /home/ whatever your login name is. I can cd ... to go up one directory, and now I'm looking at the home directory, right? /home, and it's got all these files in there, and those are everybody's home directories. And if I try to look at somebody's directory, it's going to tell me permission denied. Okay, so they're set up so only the owner can read them. If I go up one level more, I'm in my top level of the root directory /, and these are pretty much these are all the main directories that exist on the system. So /home is one of them, right? That's where the user accounts are. /bin, have we looked at /bin? So I can look at bin. That's where all of where a lot of the executable commands are. So commands like more and gzip and kill and cp for copy and rm for remove. Those are all just commands. They're just executable programs, and they're sitting in this directory called /bin. ls is a command sitting in /bin, so I can copy ls to my home directory, and I can call it haha. And now if I execute haha, that's the ls command.
Is that for all of us now, since you're in the server?
That's only for my directory, but if you could execute haha from my home directory, that would do ls for you.
Oh, weird.
Yeah. Alright, because it's just a program.
Can you give me permissions to go into your directory?
I think you have a bit of permissions there. But I have like student information for assess, so I keep it locked down. Alright, so there's all the stuff sitting inside bin. And it's a good chunk of all the commands that we use. And they're just big files. Right, so yeah, so ls is just 126,000 character file. 126K. Unix programs are usually pretty small. Right? The reason you have like megabyte and gigabyte programs on other systems is because you've got all kinds of infrastructure for supporting graphical interfaces and things like that. But the bare code for a lot of these things, I mean, some of these functions are a few thousand bytes long. Right? I mean, it's hundreds of lines of C code. There's not a whole lot going on. The whole Unix operating system is pretty small. Alright, so bin is an area where we have a lot of these executable commands. Boot is an area that's always going to be there, and when you boot up your system, when you first turn it on and apply power, and the bootstrap code starts running, in the hardware, it knows to look on your drive for a system called boot. And it looks at things like grub to control how it boots, and vmlinux is the Linux kernel, and so on and so forth. Right, so those are sort of the low-level ways that we get our system up and running. And some of these get pretty big.
Can I accidentally ruin some of your files?
Possibly, but probably not.
Well, that doesn't sound my anxiety at least.
Why, what are you doing?
I'm looking at the traffic light thing in Verilog, and I
Yeah.
don't want to like ruin it.
Just copy it. Like CP space
Yeah, but like,
and the name of mine, and copy it to your home directory, and you can do whatever you want to it.
I don't want to do anything to it. I just want to look at it.
Okay, if you just want to look at it, you can just more it or something.
Oh, that's true.
But if you copy it, then you can like look at it with VI and stuff. Or you can show me after
Man, you
class.
have everything here.
I do. All right, so boot is an area where the system files are. So what is DEV? DEV are devices. And if you look in that directory, you see a whole bunch of stuff, including a bunch of things called TTY. Some of these things are actually physical devices. Okay, so there's this idea in Unix that basically everything is a file. So FD is the floppy disk drive. Well, we don't have a floppy disk drive on the Linux server, but if we did, we could get to it through this file called FD. So if we do an ls-l, you notice that a lot of these files, they have a B or a C in the beginning. So D means the file is a directory, right? But C or B means that it's an I/O device. And C is for character I/O, B is for binary I/O. So console, that's like your main console that you use to talk to the system, even if it's not up and running, a graphical interface. FD is the floppy disk drive, which is mapped to something else. DVD is the DVD drive, right? If I did this on my laptop and I had a DVD drive, I could get to it through this file /dev/DVD. If you plug in a USB device, you'll see a new device appear under here called TTY USB 0. And if you know how to open a plain old text file and read from it and write to it, you can open up the USB drive and read from it and write to it. It's a standardized methodology for doing input and output through files, whether that's a physical file on your drive or a piece of hardware. So everything we know about interacting with files carries over to devices. All the mechanisms we have for working with files carries over to devices, right? And this helps with the expandability and portability of of Linux. And there's also there's a device called null, and that's considered the bit bucket. So you can put whatever you want into this file and it disappears, and if you try to read from the file, it's always empty. So I could copy my bash rc to dev null, and I just threw a few hundred bytes of information into the bit bucket and they just disappear. And if I try to cat dev null, it looks like an empty file.
You can bring it back though.
I did not change bash rc, I copied it.
Oh, okay.
Right, so I made a copy of what was in there and I threw it into the incinerator. And that's useful sometimes if you're doing something and it's producing output and you don't really care what the output is, you can send it into dev null and it just goes away. And I can VI it, it'll tell me it's not a file. Alright, and I can write stuff into it, but it's not actually getting written in because it's the bit bucket, it goes away. Alright, so that's what dev is. etc is where we have some system files. And so things like network configuration information are stored in here. X11 is the windowing system that lets Linux have things like mice and you can move around and stuff like that. That's a very old system that still works. PPP is point-to-point protocol. It's an old way of doing networking before everybody had routers. Password is an interesting file. It's the password file. And so it has a line for each user who has an account on the system. And so let's find Nick. So here's Nick. And it's got my full name, it's got my office number, it's got my extension, it's got my home directory, and it tells you what my default login shell is, bin bash. And this X used to be the password. So it used to be that your password would be encrypted and then they would store the encrypted file in this password file. And when you tried to log in, the code that was authenticating you would open this file, look for your username, look for your encrypted password, take the password you typed in, encrypt that, compare the two. If they both encrypt to the same string of gibberish, then it says you must have put in the right password and it lets you log in. So we don't store passwords in here anymore. Why? What would be wrong with storing encrypted passwords in here?
I think you could access them.
You can access them. Very hard to unencrypt theoretically. If you could unencrypt them, yeah, that's a big problem. But pretty hard to do that.
Couldn't you like check the history?
But kind of related to that. The reason that it's nice to have access to this is that if you want to do something that authenticates the user, like if I wanted to use Assess and have you put in a password to make sure it was you, I could take your password, encrypt it, compare it, and know if it's actually you, right? The problem is somebody who's trying to figure out your password can just brute force attack this. They can start going through a dictionary or a phrase book and start encrypting different things until they find something that encrypts to your encrypted password, and then they know your password. That's how brute force attacks work, basically. Now, if you try to do that by actually logging in, 3 failed logins and it disconnects you, you got to reconnect. Or it waits 5 seconds, and that's enough to make that intractable. But if you have access to the encrypted password, you can just rapid fire it, you can throw your PlayStation at it, and make a pretty good attack in a few hours, probably.
Seems like a lot of hard work just to like find out someone's password.
Yeah, but there's a lot of 8-year-olds out there with spare time and access to really good hardware.
Yeah.
So encrypted passwords aren't stored in here anymore. So occasionally you'll hear about a security leak, and what happens is somebody had unencrypted passwords stored somewhere and they got leaked out. Okay, LinkedIn did this years ago by mistake. So you never want unencrypted passwords stored anywhere, right? You don't even want them sitting in memory. After you change your password, you finish typing it in, you hope that the code that you're running overwrites that section of memory so that it's in memory as little as possible and it never gets stored to disk. Because if it gets written to disk, even if you delete the file, there's a record of it. And if you write it to disk and you overwrite it, if you can get physical possession of that disk, you can see what was there before the bytes got changed, right? So you can do forensic science on it. But it turns out machines are fast enough now that even if the passwords are stored encrypted, if someone gets access to that, it's considered a potential problem. So most of the leaks that you get emails about today are, you know, somebody got access to encrypted information. We recommend you change your password.
So is that X a placeholder? So it is like
I think it's just a placeholder because there's code that, you know, wants to find out my office number, so it skips over this many colons.
I see.
And so it doesn't break anything that worked before.
Cool.
So where are passwords stored?
Somewhere. So I'm not up on what the current practice is. It used to be set up on software network type of thing. I don't actually know where they reside anymore. So YP password took over password. It was the Yellow Pages password. And it was just hashed somewhere where it was protected. So you can still get to this information as just a regular user, but the passwords were in an area where the file wasn't readable unless you had root access. So there's different levels of security. So ETC has lots of good stuff in it. Including a file called protocols, which tells us what different port numbers do what. Actually, services is a better one. So we'll talk about networking maybe a little bit this course, but definitely in 223 in spring we'll play with this file. But basically, if there's a machine on the internet, theoretically you can connect to port 37 and talk to its time server and find out what time the machine thinks it is. Or it used to be if you wanted to send mail, you could connect to port 25. That was a simple mail transport protocol, SMTP, and you could start a dialogue and send mail to somebody on the system.
Is this for like internal systems?
This is for internal, but it'll actually work on some external systems. Now, most of these things aren't used anymore. We use secure versions of them. But when you connect through PuTTY, for example, to the Linux server, you're running a protocol called SSH. You're making a connection to port 22.
Huh.
And if you look at PuTTY, if you look at that initialization window, in fact, it's worth doing this. Let's just start PuTTY. Takes it a second because it's emulated. So on this PuTTY window, under port, it says 22. That's that 22 right there. We're trying to use SSH. If I click on Telnet, it says I'm going to use port 23. That's this 23 right here. Telnet. And I can connect to any port I want.
What happens if you log in the server now?
Well, let's see. Let's just go to linuxengrcs.com and let's try port 37. And it sits there and it's probably waiting for me. And I don't know how to talk to the time server. So it used to be you could go to port 79 and that would be like running the finger command. So finger is kind of like who, but it gives you more information. It'll give you the full name of people if they've given a full name, tell you how long they've been idle, and so on and so forth. And so you could talk to port 79 on a different machine and see who is logged into that machine. So this is like the early stages of what today is the internet, right? This was just like different protocols, some of them experimental, usually on small clusters of machines on a local intranet. But this backbone is still what everything is built on, right? A protocol called TCP sitting on top of IP, and we'll definitely play with that a lot in 223. So that's more of the stuff that's inside this etc directory. There's a lot of networking support. All right, files. USR. So USR is sort of the user area, and it's got its own bin directory. It's got a games directory. It's got an include directory, which is where things like stdio.h are. It's got a lib, which is where certain shared libraries are. So if you want to use the square root function, you say -lm, you're actually asking for a file under /user/lib. And there's other directories. There's source. There's local for files for things that are local to the system. So there's some of the games that are on a system. So most of which we've already talked about. So that's just a little bit about how things are organized. Doesn't have to be that way. That's how it is on Linux, though, right? And things expect things to be in certain locations. So if you look at your variable called path, it's a list of where it should look for commands if you type in the name of a command that it doesn't understand. For example, cowsay. Where is it going to look? Well, it's going to look under user local sbin. If it doesn't find it there, it'll check user local bin, then user sbin, then user bin, then sbin, then bin, then user games, and that's where it's going to find it. And so it'll grab user games cowsay and execute that.
Can you show me an example of that?
So if I say which cowsay, it'll tell me where it's located. And if I look at /user/games, there's cowsay sitting in there. So I can say user games cowsay to execute it. But if I just say cowsay, it also executes it. Why? Because it doesn't know what cowsay is. It's going to check each of these directories until it finds it, and it's going to find it right in here. And so it executes the one from user games.
Does that go for any programming, right? So like
That's pretty much any program, anything that you type in, unless it's understood by bash itself.
it will just automatically find it somewhere else.
It'll look for it somewhere else. So if I say pwd, that's something that bash understands. Okay, that's executed by this program called bash that's running right now. But if I say, ls, that's not part of bash, right? Which ls, that's something sitting under /bin.
Huh.
When
So
I
you could
say
put, like,
who,
Hooch.
that's something under user bin. If I say which, that's another program under user bin.
Where's finger?
Probably user bin. Alright, so most of these things are just files. CD is not a program, though. I can say what is, can't say what is.
Nothing
Right.
appropriate.
Yeah, there's something that'll tell me it's a built-in command. Can't remember what it is right now.
Built into bash.
So that's
Yeah.
why you're able to create programs for us on the Linux server, and we can just do whatever.
Yeah.
Even though we can't see where it is, we can call it.
Yeah,
Exactly.
so assess is under user local bin assess, and that's part of the path. But the assess command is actually a link. We're going to talk about links another day. It's actually a link to this file homenick assess. So it's actually pointing to something in my home directory, or under my home directory. All right, does it make some sense?
Yeah.
All right, here's another good command. Okay, so here's a function I wrote sometime past few days, probably called pick.c. and we compiled that into this file called pic.o. And pic.o looks like gibberish to us. Right? If we try to VI it, it's 2 lines of stuff. And here's an executable program called pic that's 15 lines of gibberish. Okay, if you want to look at a file that you can't look at easily in VI or by saying cat or more or something like that, here's a useful command, xxd. So xxd followed by a file name says, give me a hex dump of this file. And it gives you a really nice and clean output picture like this.
Those memory addresses on the left?
So on the left are locations in the file. Could be memory addresses, but this is just a location in the file. So byte 0 is the first byte. Byte 10, this is all hex. This is byte 32 on up. This is starting from byte 64. Right, so showing us 16 bytes per line. A byte takes 2 hex characters, so we should see 32 hex characters per line, 8 chunks of 4. Okay, so 7F, that's what's stored at location 0 in the file. That's an unprintable character, so it showed me a dot. The next thing in the file, location 1, is the binary pattern 45 hex, which is the ASCII code for E, so it shows me the letter E over here. So over here I'm seeing the hex values of each byte in the file, 45, 4C, 46, 0201. And over here I'm seeing either a dot if it's unprintable or the ASCII value if it is printable. And this is a pretty easy way to go through and find, some stuff that's human readable. And to look at things that aren't human readable, but you may want to know what's the actual byte value stored in this. And if you want to see this one page at a time, you can say pipe, vertical bar, pipe this into more, and it'll show you the output one page at a time.
Why are there so many spots where there's just zeros?
0 is a popular number.
Okay.
So it's most likely just filler between stuff that needed to be in one spot and in another spot. And it could have been filled with anything. For example, this stuff is human readable, right? This stuff is not. But stuff sometimes needs to be aligned on certain boundaries. Like we don't usually pack everything in right next to each other in a file because it's easier to process the file if you say, okay, we're going to have this much space for this, and if we don't use all of it, you just fill it in with zeros.
Oh, so it's like having an array with 120 characters,
And you only use 10 of them. Yeah. Yep.
Gotcha. Can you rely on it putting in zeros for those remainder?
No. But it depends on the file, right? So, so here's a WAV file, okay? Right? So what is all this stuff? It's music.
Apparently it's a riff.
And you can tell there's something interesting because there's not a lot of the same stuff in here. In the beginning there's a lot of these caret @ signs. Well, those are zeros. That's how it prints out in VI, right? But if I XXD this and run that through more, I can look at this in a more controlled way, right? The beginning of the file is riff star 1, RIFF star 1, and then there's a CB02. Well, that I believe is the total file size, or something related to the total number of bytes. And then wave is a tag saying this is a wave file, and so on and so forth. And you can find these. Right, so this will tell you what a WAV file looks like. It starts with RIFF, and then there's 4 bytes, which is the chunk size, which tells you how big this thing is. And then there's a format field, and if you read later down, it will tell you that format is data or something else. And you can take the binary stuff inside a WAV file and understand what it is. And it's a chunk of header, 44 bytes worth, followed by just a bunch of data. And the data, the size of each piece of data depends on what's specified in the header, but usually it's 16 bits to specify a sample from the left channel and another 16 bits to specify a sample from the right. And your sound waveform was just chopped up 44,100 times per second into 2 channels, and you just store those channels next to each other. So after 88,200 of these data samples, you've got the first second of your music. And if you got a WAV file in your system, you can open it up, you can use this, you can use XXD to study it, you can read it in, you can change it, write it back, and then play it. If you want to make your song play backwards, you can do that with a C program. Just open up the file, read it in, write it back out in reverse order, and you got a backtracks file.
Elon and Diaz.
Yeah, exactly. That was good.
SLP?
Yeah. A lot of good processing you could do for an SLP, I think. Because, so how many people here use Audacity? Gotta use Audacity, man. It's like the best sound tool for like chopping up sound and stuff like that. It's got all kinds of filters and effects inside for adding echoes and removing distortion and amplifying and speeding up and slowing down without changing tempo and so on. That's all it's doing, right? Just reads the file, pulls it into memory, and does stuff with it with, you know, a big old C program, and writes it back out. It's got a nice graphical front end on front of it, on top of it, and so on. But it's just data.
When you're modifying data with Audacity, does it use the entire thing including the header, or does it just start with the data set?
It's got to use the header to know how to interpret the data.
Okay.
Right, because things you have in here is, for example, how many channels do you have? Is it mono? It's 1. If it's stereo, it's 2. What's the sample rate? Typically 44,100, but you might have a low sample rate, 16,000 or something. So it uses all of this to figure out how to interpret the data.
So if you're dumping like 8 different sound files into Audacity that all have different headers, where does it store it then?
Somewhere in its internal memory.
And like if you do that and then you save the sound file as like one thing, what happens to the header then?
So Audacity gives you options for like mixing your tracks together, and it lets you specify things like bitrate and stuff like that. And you know, somewhere a decision has to be made, how to, you know, what information you want to use to write it out. Bitrate, number of channels, do you want to compress it to be mono, and so on and so forth. But it's all just code manipulating data.
Interesting.
All right, so that's not on the exam, but it's good stuff to be talking about because this is something I want you to come away from Clark with, is this idea that none of this is magic, right? I mean, we parts of it are magic, but the parts that actually like change things or manipulate code or make the computer do the things that we expect it to do, that's just programmed, right? And it's just programmed with stuff you already know how to do, right? If you had enough time, you could write a program that would, you know, take a WAV file and turn it into a file that plays backwards, right? You'd have to figure out the algorithm, and there's a lot of mechanics involved in dealing with large amounts of data. But, you know, read this, put it there, read that, put it there. It's like your palindrome program from 121, just applied to a WAV file, same idea. And you can get the computer to do whatever you want. All right, I'm going to leave it there instead of like going into a really boring discussion of like more Linux commands for 2 minutes.
It wasn't that boring.
All right, so don't forget to turn in your PA2 by 8 o'clock tomorrow. And we will talk about PA3 tomorrow. PA3 is going to be back doing a shell script, bash program. Okay, we'll be programming a game in bash. So we'll talk about that tomorrow.